Hello, my name is Carsten, OZ9 Alpha Alpha Radio, and this video is about configuring the dual RF head together with the REPAM module. This configuration is something I've been asked a few times from users. It's probably one of the more complicated things in the REPAM configuration, but I hope this video can shed some light on how it's done in a real setup. First, a little bit of background information for the dual RF head. The dual RF head is a logarithmic amplifier or detector. Basically, it measures RF on 2 ports. The sensor has 2 port A and B, and the signals on the A and B ports are amplified and passed through a logarithmic detector and output as 2 analog voltages. Usually the forward power is input on the A port, and the reflected power is input on the B port, although you could swap it around, but that's the way it normally is. The dual RF head can measure from around -50 to 0 dBm. So normally you connect the forward and the reflected power to a directional coupler. You need to be careful that the directional coupler has enough attenuation on the forward and the reflected port, as if you exceed the 0 dBm, actually it's plus 10 dBm, but if you exceed that, you might damage the input circuit of the dual RF head. So take care and be sure that the directional coupler is not outputting more power than plus 10 dBm. If it does, you need to put an attenuator in front of the A and B input. So you put maybe -10 dB or whatever is needed on both of the ports, so you don't kill the dual RF head. The dual RF head delivers approximately -55 millivolts per dB. Now that sounds maybe as a funny value, -55 millivolts. The meaning of that is that the voltage will get lower from the dual RF head the more power you put into it. So let's say that you have a system where you have a directional coupler connected to the forward and the reflected. The forward power is A and the reflected is B. And if you look at the voltage on the output of the dual RF head, and there is no power flowing, I mean the output power is 0, you will typically see it's not the correct number, but let's say it's around 4 volts. So you will see around at let's say at 0 watt, you will see approximately 4 volts on the outputs. Now pay attention that when I say power of 10, 50 or 100 watts, that is on the directional coupler. It is not on the input, because as I said, you will kill the dual RF head. You need the directional coupler, and maybe you also need an additional attenuation on the inputs to put the levels between to put the values in between -50 and 0 dBm. So if we again apply 0 power to the directional coupler, that is the input on the A and B on the dual RF head are are at 0 RF, you will see around 4 volts on the output. And if you increase the power through the directional coupler so that the power on the A and B input rises, you will see the voltage on the output get lower and lower and lower. Depending on the attenuation and the coupling in the RF, in the directional coupler, how much power you are running and so on, the voltage will go down to maybe 1.5 volts or something at full power. The 1.5 volts in this case will correspond to around 0 dBm on the directional coupler. And this is just to explain how the minus 55 millivolt is to be understood. Let's say that if you have, let's say you measure 4,000 millivolts on the output. Let's say you have you have 1 watt through the forward port on the directional coupler. If you then increase the power and you measure a voltage of, let's say, what is it, 3,445 millivolts. You have, I hope, you have a difference of 555 millivolts. Yeah, bad example, but you get the idea now. This is approximately 10 dB. You see, you have around 550 millivolts, and you know that there are 55 millivolts per dB. So this is a delta of 10 dB. So you know that if 4 volts on the directional or on the output of the dual RF head correspond to 1 watt, you know that 3,440 millivolt correspond to 10 dB more, that is 10 watts instead. This is basically how the dual RF head is working. It gives you an analog voltage that will increase or decrease with 55 millivolts for every dB you change the power to it. This is the basic, and both the A and B channels on the dual RF head works exactly the same way. There are no differences. So with the theory out of the way, I'm going to start the REPAM monitor application. The REPAM monitor application is can be downloaded from the REPAM website on www.moonbounce.dk. The program looks like this when started the first time. The first we need to do is to locate the REPAM module. The REPAM module is powered on and connected to the same network as the PC the REPAM monitor is running on. And in my case, I have a simulated setup where I have a variable voltage I can input to the REPAM to simulate the dual RF head, but the basics are the same. First, I will locate the REPAM module. I double click to select it, and we should immediately begin seeing data coming in from the REPAM module. Now, there are many things you can set up on the REPAM module using the REPAM monitor program. I won't go into details on most of it. I will just concentrate on the dual RF head setup. The other settings can be seen in the user's manual and some other videos I have made also. So we go into REPAM settings. It is a complete default setting in the REPAM module, so nothing has been set. In my case, I have connected a dual RF head to analog input 1. This is what I call the forward port. Analog input 2 is what I call the reflected port. I give some symbolic names to these two inputs. This makes it easier later on to identify where the ports are and which port are used and so on. You can do that on all analog, digital I/O and temperature sensors and so on. You can give them symbolic names. I go to the OZ9IAR dual RF head tab here. Right now it's disabled. The first thing I do is I select the forward port to be AI1 and the reflected port to be AI2. Now, this is only a setting that is seen on the PC, so I need to push it down to the REPAM module to get live data. So first I do this write to REPAM. Are you sure? Yes, please. And I go into the settings again, and you now see that the analog values from the AI1 and AI2 ports are being shown here. Those are the same as you see on the main screen here. So the first thing I need to do is disregard these two forward coupling factors. This is if you at some later point add additional dampening, you can enter that here to correct it, but let's not go into that at the moment. The first thing we need to do is you have your directional coupler, and you need to be able to put some power through it in the normal forward direction, and you need to be able to put some power in the reflected or in the opposite direction. In this case, I have connected the setup so that I will send some power through the normal forward direction. And the way you do it is that you apply a known power. In our case here, we could say that that the low power will be 1 watt. So I type in here 1 watt. I could also do it in dBm, depending on how I measure the true power going through the directional coupler at the moment. But let's say that I have a watt meter at the output that I trust. So I say I have adjusted my transmitter to 1 watt, and if I'm transmitting 1 watt, I would probably see a voltage of, you see here, around 3.7 volts or so. If you remember the graph I showed before, a higher voltage means a lower power. So let's say we are around 3.7 volts right now. I'm applying 1 watt through the directional coupler, and the dual RF head outputs around 3.7 volts on the A channel. When I know that I have 1 watt, I press this one. I get a warning. It will now calculate the number of dBms and read the forward voltage on the AI1 port. Are you sure you want to continue? And I say yes, I will. So in this case, the PC program takes a reading of the analog input, 3.780 volts, and stores that as the minimum power. And that's it. The next step, I need to go to, let's say I go to 100 watts. At the moment I apply the 100 watts, I will probably, the voltage will probably get down to, let's say 1.6 volts or something like that. That's a good approximation. And again, I press use, and it tells me I will now calculate the number of dBm and take a reading of the analog input, which was 1646 millivolts. So this concludes the setup of the forward calibration, and it's pretty easy. Use a minimum power and a maximum power, or the highest power you can do on the directional coupler. The further the distance is between the two, the more accurate it will be. If let's say that you have a forward or a directional coupler where you're going to measure, let's say 500 watts, and you do the minimum power at 1 watt and you do the maximum power at 2 watts, it's clear that if you then apply 500 watts, if you had a small error between 1 and 2 watts, the error will be very big if you go up to 500 watts. So choose the minimum and the maximum with the largest possible spacing to get some more accuracy in the reading. This is now done on the forward port, as I said, and the next step is that that we do it also on the reflected port. On the reflected port, normally you would not have the full power. Some uses, let's say, 1 watt at the minimum. Again, we say use. It will take the voltage here from the reflected port, and remember that. And let's say that that the maximum reflected power is, let's say we apply 5 watts. In this case, we have of course swapped the in and outputs on the directional coupler to get the power on the opposite direction. Again, the voltage went down to 1.6 volts. We press use, and it takes the voltage reading there. Now you can see on the forward calibration, we had for 100 watts we had 1.6 volts, and on the reflected we had for 5 watts we have 1.6 volts, and that's because that a directional coupler can sometimes, it will not have the same coupling factor on the forward and reflected ports, and if it does, usually you would put more external attenuation on the forward port than on the reflected, because hopefully we are not going to measure the full power on the reflected port. If we have a PA with let's say 100 watts, you would not expect to receive 100 watt on the reflected port. That will be pretty bad. So normally you lower the attenuators so that you maybe get full the full level of the dual RF head at maybe 25 or 50 watts, or some place in the neighborhood of that. So I did the minimum and the maximum power for the forward, the minimum and the maximum power for the reflected port, and that's it. I'm basically done now, and in order to, this is only done on the PC, so in order to put it to the REPAM module, I press again write to REPAM, and if we go, we can go in here again. It's a bit easier to see the data here, and now I will connect both ports of the dual RF head, and when I adjust the input voltage, you can see that the power is being calculated, and the SWR is also calculated all the time. The variable voltage I put in now is the same on the forward and the reflected power, because I'm simulating it. But in a real life situation, you would see different voltages, of course, on the forward and the reflected. If we go down to, as an example, around, let's see if we can hit 1640 something, close enough. You see that we have a voltage reading of 1.65 on the forward port, and we told REPAM that 1.646 is 100 watts, and right now it's reading out 99 watts, or almost 50 dBm. And the same on the reflected port. We told it that 5 watts was 1646, and it reads 1652, so that's close to 5 watts. And if I can try, and you can see if I go below, down to 1200 millivolts, the power is actually higher than what we calibrated, and that is fully legal. There's nothing wrong with that. And again here, you see we are at 1265. We know that 1646 was a 100 watts, and the calibration values I used here gave actually a slope of minus 106 millivolts per dB, which is of course wrong. As I just told you that the dual RF had outputs around minus 55 volts per dB, but millivolt per dB. But the basics are the same. The numbers are just wrong because I'm just simulating. But I hope you get the idea here. So this is basically how it's done. And the numbers here, again, as I said, the higher the voltage on the dual RF head, the lower the power. You can see the voltage going down and the power goes up. So this is basically everything that is to it. And then you can of course go to the trigger menus and set up all kinds of alarms. You could say that if the SWR exceeds 3, you would have an output, digital output 1 to go off. That's one of the relay outputs. Or you could have it go off or give a pulse of 1 second or whatever you want. There's a huge number of things you can do. You could also say that if the forward power exceeds 150 watts, you would get an alarm, and so on and so on. There's a lot of things you can do there. But again, this is out of the scope for this video. We focused only on the configuration. Again, apply the lowest possible power on forward, enter the number of watts, or enter the dBm value and press one of the buttons here. When you press the button, it will read the value, the analog value on the inputs, place it in one of the boxes here, depending on which if it's a minimum, maximum, forward, or reflected you are doing, and that's it. And remember to write it to the REPAM module at the end. That's pretty much it, and I hope it gave you an idea of how to configure the dual RF head in the REPAM module. Thanks for listening, and good luck with the projects.